So, welcome back, guys. This is lecture 3 on unit 4, the design part. So here I'm with you to explain. So we actually in the previous section we have discussed the proportional controller, PD controller and PI controller. And then what is the make sure that how the lead, why the lead, lag and lead lag came to the picture. So just before going to that, what we happen with proportional controller, we just simplest to implement. It is simplest to implement and may not sufficient to meet the design requirement. That means if a design required high transients and steady state error, they may not be required, but it improves some stability to the system. Now while coming to PD controller, this also improves the stability. Okay, since the proportional is there, increase the stability, but increase the transient response for the PD controller. So that means improve the response means transient response, and provide controller to the more over pole. Just you have to look on this. Now while coming to PI controller. So PI controller gives a perfect tracking of the constant reference inputs. That means improve the steady state error. That means steady state error is improved. Okay, so steady state error is approximately going to increase 0. That is called perfect tracking, and this also gives the rejection of constant disturbance inputs. Okay, so these are the advantages of PI, P controller, PD controller, PI controller. If we incorporate 3 controllers, so eventually we get the stability got increased, and we have control over pole locations means transient improvement, and again perfect tracking of the constant with reference inputs, and constant disturbance rejections will be get by PID controller. Okay, we have this PI for the reduction for the sake of our stability increasement, transient increasement, and steady state error. So what is the point of lead lag? So in implementation, we have some defects in PI controller, PD controller and PID controller. What is the issues is, we know that PI controller provides perfect tracking for the constant reference inputs and help in rejecting constant decimal disturbance, which I have seen. But we have seen that the PI controller is not suitable system, leading to a destability of a closed loop higher order system. Say before we have seen system like G of S equal to 1 by S into Ts plus 1. Okay, so for this if we increase PI controller means what happening? So extra poles are increasing, it's getting into instability. Okay, so this is not required there. So increasing the PI means even though it gives a steady state error equal to 0, it leading to instability. There is a problem there. Okay, to overcome that problem, so moreover the small so if some compromising is there involving. So even though we are getting, by using PI controller, even though we are getting steady state error equal to 0, so we have some compromise on steady state error. So that means if a small steady state error which is near to 0 is maintained and leading to a lead controller, so this lead to as a following approximation. That means we do approximation to ensure that exactly steady state error equal to 0, but near to 0, where here if you see carefully, this is PI controller, Kp plus Ka by S and Ka by Kp by A. So further solving we get. So we just we have incorporated this P here. If you observe here, if you look at this solving, we just added one pole here. So how can we add something pole with our thing? So in design we have seen that if you see this, if you want to plot this pole here, so what actually means pole at origin, see this is a pole at origin, right? And we have some pole, something pole 0 here. Now what we are doing is, we are slightly moving this near to origin, we are keeping another pole. Okay, that is lag controller. So near to origin, in spite of at origin, we are placing this or this here near to origin, and we are remaining this 0 here only. Okay, so this leads to this increase approximation of adding a pole which is near to origin in spite of origin leads us where P is very close to 0. Further, this gives a lag compensator. Okay, so keeping in the mind that if you increase SS poles at origin, this leads to instability. We have seen this previous section with root locus and all, if you have remember. So we just involving not only keeping poles at origins, we are keeping a pole near to origin which gives a lag compensator. Okay, so instead of pole and origin is 0, we have pole and 0 in the left half plane, and the controller is stable. Okay, so this is the meaning. So in general, so that means for a lag compensator, we should simply have to keep in mind we have a pole at near to origin and 0 at far away from the origin. This is the lag compensator, right? So in general, in S-plane, if you want to describe the lag compensator, I will give this order where ZC is minus 1 by T and PC is minus 1 by beta T, where T is a time constant and beta is greater than 1. So here beta, if you want this 1 by beta is called attenuation factor. So we'll know what is this shortly. And beta, if you substitute this thing, so beta, if you want beta means, so ZC by PC will get this. So we realize this lag compensator with so you know that every transfer function, behind every transfer function there is a circuit or there is a mechanical system. Since we are electrical guys, so we need this lead compensator has a mechanical things. In spite of resistance, we have a spring ram damping thing and a capacitor. We have mass and etc. We have dealt in first unit about analogy between mass and electrical things. Now we are realizing the lag compensator with the electrical circuit. So I am keeping this input EI of S and output is G of S, where output is taken across R2 and 1 by SC. So by voltage division rule, if I make sure, so since we are experts in circuit calculations, we got E naught of S of I of S. So further solving, so my mind is thinking about this. So while solving this, my mind is thinking about getting this equation, right? S plus Z plus S plus plus. So for that, what I get is this thing. Okay, so further this, so S plus, if you see this S plus 1 ZC, S plus I got this, right? So ZC, so further moving, I got this function, so S plus 1 by T, and this is the, so further we'll get, so here I got time constant T equal to R2 by S, R2 is R2C, and beta value, so I got R1 plus R2 by R2. So substituting this. So this is a physical realization, okay, of a lag compensator. So if you want to, for this lag compensator, I want to design the frequency response. So how we'll get is, so same, so for any individual lag compensator, if you dot the phase margin, Bode plot, if you want to magnitude plot and phase plot. So if you see here what I'm involving has, we have pole at origin and 0. So here first corner frequency is pole. That's why from up to certain point it is 0 dB. At some corner frequency, this is 1 by beta. This is less than this. So I get pole at near. So here minus 20 dB I got. For up to a corner frequency of this is 1 minus 1 by beta T, and this is 1 by T. At this point, again what I'm adding is 0 is adding. Okay, so this is the magnitude plot of this lag compensator, and if you draw the phase margin is tan inverse of omega t. So tan inverse of omega t, So omega t, so if you substitute s equal to j omega here, omega t minus tan inverse of omega beta t. So obtain this is a phase margin. Now our main thing is in design, so we'll already have a transfer function of g of s, right? So something if you do, so if you g of s transfer function, I obtained magnitude plot like this and phase plot. Now what we are doing is we are cascading this obtained Bode plot. So if you may Bode plot, if I draw, it may be of lag compensator. What it may be like this. Okay, now this is compensator Bode plot and this main plot. After cascading, we get g of s. This is called overall transfer function. For that overall transfer function, I may approach something like this. Okay, this is called compensated. So compensated overall transfer function. So what we are doing is, for our requirement for any values, we are changing the magnitude plot of given system to obtained transfer function. So we are increasing something called phases. So by incorporating some phases, so to understand that, we mainly need something called maximum phase angle. Okay, so the maximum phase angle is occurred at a point that is omega m, which is called frequency of maximum phase. If you see, this maximum phase will go to a certain value and again decreases. So we have to find maximum phase. The phase at which the maximum phase is occurred is called maximum phase, and the frequency at which we call the maximum phase. This is a geometric mean of this thing and this thing. So we have some calculations how to find omega phi m. So in this lag compensator, mainly we need to find phase angle and frequency at that maximum phase angle and this beta value. Then we'll get this function. Okay, to get this lag compensator, we need to find phi m, omega and beta m. So only simple need is, for a given system, if we incorporate some phasing, so new compensated will get, that new compensated will get based upon our required specifications. So we'll solve shortly, right? So this is determination. So I just said that to find omega and phi m beta, this is a calculations part thing which I already done. So just make sure to do this. So I got this phi m equal tan inverse of omega t minus tan inverse of omega t. So if you differentiate this with respect to omega, so why? Because at this point the phase is getting 0. So changing, sudden change means differentiation of that is 0. You already know that. So if you do that, so I got something. So this is all calculations you have to do it at your own. So I got some relation between omega m and t. So I got this equation, right? So if you do that, so I don't want to disclose that. So all these things, just have a look. I just did that. So this is the equation in tan inverse. So this, I already know that differentiation of tan inverse is 1 by x square. So tan inverse 1 by omega t square, and this is x is in this. Again we have x dot t. So omega t differentiation. Omega is our differentiator. So differentiation of omega t is t and minus of. So this is getting 0. So this get transferred, and finally I obtained the equation. So at this point, if I substitute omega equal to omega m, so I just changed this here, up from here the omega value to omega m, and make this, and finally I got this equation. Okay, so I got equation omega m in terms of t and beta. Now if we substitute omega m in this equation, okay, so that means the value of phi m, now if we substitute this in this equation, we'll get the value of phi m, okay, the value of phi m at omega m. That is the meaning. So if you substitute that, I get this equation. Okay, So you just substitute that and find this equation. I get phi m something called this. If you draw in triangle the hypotenuse thing, I get sine phi m in form of 1 minus beta by 1 plus beta, and finally from this equation I obtained beta equal to something called 1 minus sine phi m. So we need this equation, 1 minus sine phi and 1 plus. So overallly, so with omega m value, phi m value, and we get the beta value. So this is the thing. So okay, so just want to make sure how you got beta value and phi m value and omega value. So we'll use this later. Okay, so this is about lag compensator. Now let us go to something called why we got lead compensator into the picture. In similar fashion, what are the issues we face in PI controller? In the same form, in PD controller, which has a major problem, that is, in general, PD controller means proportional plus differentiator, right? Proportional plus differentiator. So this has some function, right, which improves the transfer function, and this improves the something called damping thing and increases the transient response. We know that, but the major problem is that system is, in general, the system is non-causal. What is non-causal means? So causal system is something which depends on present and past inputs. Non-causal means which depends on future inputs. Since we are not, we are working, so we can't realize the circuit. Since the transfer function, if any transfer function should have, so if I have n of numerator by denominator, so my denominator poles should be greater than 0. So if you see here, for this function there is no poles here. Our job is to incorporate something poles to realize the system, right? Either we have to make p equal to z, or we have to make p greater than z. But here for this function, z is only there but no picture of p. So this is not physically realizable. To get realizable, we just incorporate something called poles here, right? We incorporate something called pole here with some approximations. That is, we are incorporating pole which is far away from origin. Okay, so if we incorporate far away from origin means there is less impact on the system. You know that when any pole which is far away from origin, we have less impact. Okay, so we are doing that. If you go the math calculation for this system, if you draw with you, so just TDS is a causal, and with P tends to infinite, and TDS equal to, TDS means differentiation to KDS, and we recover the controller. Total PD approximation lead to, so approximation of PD by incorporating pole at infinite will lead to lead compensator. Okay, so what is just the difference of lag compensator. Here the lag compensator, we are incorporated pole at origin, near to origin. Okay, so approximation to pole at origin, we are incorporating pole near to origin. Here we are incorporating pole far away from origin, which has less impact on the overall system, but should be, why we are incorporating pole means to get realizable. For non-causal system to causal system, we are adding lead compensator. Okay, so you see, even though without approximation the results are common, but to physically realizable we are doing all this stuff. Okay, we have to make sure of this. So similarly with all this math you get some same form of like lead compensator, but there is a difference that here so you just read all this stuff that is useful for you, make a note of that, but I am discussing this here. So we are having a pole at far away from origin here, then ZC is now we are making it minus 1 by t, and PC is minus 1 by alpha t. If you look carefully here, the pole here, in this pole we make sure that minus 1 by beta t. Here the pole is minus 1 by alpha t, where alpha is less than 1. Here beta is greater than 1. Okay, so to get, if alpha is less than 1 means this value will be more than this. You have to understand that. Okay, so alpha is called attenuation factor and 1 by beta is called attenuation factor, where that is leads to alpha equal to 1 by beta. Okay, so both are attenuation factors. For to get alpha, we have ZC by PC. Okay. Now, physically realizable, similarly to lag compensator, we can physically realize the lead comper as well. We can physically realize the lead compensator as well. In exam, someone asks you to realize the lead compensator. That means you have to draw the circuit with simple circle with the electrical calculations. So I was very much fascinated to use voltage division rule. So in basic circuit analysis, you all know this thing. So for this, V naught equal to what? R2 into, so I want to say, so if you're having two things in series, that is R1 and R2, if you have any voltage source, so voltage across R2 is what? V2 equal to supply voltage into R2 by R1 plus R2. So the same thing we have did here. Okay. So the supply here, this is our V2. So to get the voltage across this, I did this after final calculation. My main aim is to get S plus ZC plus S plus PC. That's in the form of time constant. I obtained something this like this, where the time constant T equal to R1C and alpha value is here R2 by R1 plus R2. So it is, which I just said that alpha is 1 by beta. So I get the beta value something different one. Okay. So similarly to the frequency response of the lag compensator, we have the frequency response of the lead compensator, which is completely opposite of the lag compensator, where because we have for the lead compensator, we have pole at origin and pole near to origin, sorry, 0 near to origin, pole at origin. That means my first frequency will get pole 0. That means plus 20 dB. Okay, and this is after reaching this corner frequency, that is 1 by alpha t. This is 1 by t. This is the first corner frequency where I'll get 0, that is plus 20 dB magnitude. Okay, after at this corner frequency we'll add 0 pole. So we have to make sure of this. Okay, so this is again the phase margin. So here again the maximum phase occur at frequency at omega m. So if you make note of it, so up to this we have the magnitude value 20 log 1 by, so we have to use something there. We'll use this something 20 log 1 by, so what is the factor which will incorporate to the main system while design. Okay, so you'll understand shortly with the next video I will make. So where I'll design the lead compensator with this. And similarly we have value of this thing. So the small bit, so up to omega 1 value, the small bit is 20 log 1 by beta p. The total one is 20 log 1 by beta. Here small magnitude value is 20 log. So we'll call this attenuation factor magnitude 20 log 1 by 20. So we'll use this so something in the design thing will shift the, with this only factor only will shift the magnitude plot of overall system to something. Okay, so we all understand that. Okay, this is the phase m value. So now again our job is to find omega m, phi m and alpha. Okay, so I'm doing that. So if you do that, I got this something called differentiation of this. Again the differentiation of this I have to make to 0. I got omega m equal to 1 by t into root alpha. This is in general we can directly find the geometric mean, that is omega m, if you want to omega c1 into omega c2. So what I'll get is 1 by t into 1 by alpha t. So finally obtained so t square alpha, so alpha root t. So similar to this, okay, or we can directly calculate this. If you substitute omega m value in this here, that will get phi m value. that is phi m value obtained base. So again we get alpha equal to 1 minus sin phi m by 1 plus sin phi m. Okay, so we need this equation. We need this equation alpha, and how we alpha got after derivation on this. Okay, now again, so we have deal with lead compensator, we have deal with lag compensator. Now what about lead and lag? Why this lead and lag came into picture? So we have PID controller. Okay, so we have provided the approximation for both PD controller and PI controller. Now if we incorporate PID controller, that leads to cascading of lead lag approximation. Okay, that means this is called lag compensator and this is called lead compensator. Okay, if this is the pole at near to origin, so these two parts lead gives us the lag compensator, and these two parts will give us lead compensator. After cascading these two things, that is PI and PD, will get PID, so will ultimately lead to lag compensation. Okay, this lead lag part, lead part, so beta is greater than 1, and to realize this lag lead, okay, so we'll just incorporate this whole lead lag. So if you do, after finding lead lag compensator, lag lead compensator, so by this PID means complete bonanza, that will give, which will give you the stability, steady state error, as well as the transient response. Okay, so we'll just, if you incorporate lag lead means, which will give you what, the steady state error, will get steady state error improvement, transient improvement, and stability also. Okay, so this is the physical realization for lag lead compensator, where these things, so the idea of to get is these functions, two functions. Okay, so obtain this, if you draw this, so after doing all this thing, so we have already know the picture of this. So after calculating this, we substitute these, after all, we also realize this, if you look carefully. So after deriving this, we substitute these values here. I obtain T1, T2. Okay, this is the final equation of this equation. We already know the lead lag compensator, and we derived this equation in the form of this equation to get T1, T2, and beta alpha 1. Okay, if you understand that, so T1, so in this place of T1 I am having something called this thing. Okay, so this thing, and in theta 2 in the form of this thing, and 1 by beta, so 1 alpha beta T1 T2 in the form of this thing. So alpha beta is T1 T2 plus R1 R2 C1. We got this. If you substitute T1 T2 here, I get alpha beta equal to 1. Okay, this gives alpha equal to what, 1 by beta. You have to note that. Okay, so this is a realization. Again, if you want to draw the frequency response of lag lead, so what is that? So it's simply this is a lag compensator and this is a lead compensator. The cascading things will give us. So here we'll incorporate. So here I have a pole 0 0 pole. This is up to here lagging. This is lead. So first corner frequency I'll get 1 by beta t, and this T1. This is 1 by T1, and this is 1 by T2, and this is 1 by alpha T1 T2. Okay, so for 1 by beta T1, 0 is added. Sorry, a pole is added. It is minus 20 dB. Okay, pole gain dB is minus 20 dB. So up to this 1 by T1, now 0 is added, minus 20 dB is nullified to plus 20 dB, you will get straight line. Up to theta 2, what is added? 0 is added, that is plus 20 dB. Up to what? Up to this corner frequency, we get again minus 20 dB added, plus 20 dB minus 20 dB gives or straight line. Okay, so for this I'll get the phase something like this. Okay, we will incorporate this system, so as I said, to the main system to get our design specifications. Okay, so this is a lag lead compensator. So finally So this is the main thing I wanted to assume. So PI means lag controller, PD means lead controller. Lag will improve the stability performance, and lead will improve the transient performance, steady state stability performance, and PID will give the balance of lag, lead, improves the both transient and steady state response. Okay, so this is about approximations of PD PI controller, and there's physical realization and the finding the maximum phase angle. So in your mind you have to fix two things. So mainly thing is maximum phase angle, which occurred at maximum frequency, and we have to find the values of alpha, beta. Okay, so this is about so in the next class we'll deal something called how to design lead lag lead compensators by frequency response. Okay, what is the main idea in design? Thank you guys.